From this time, we continue to discuss about the basic concept of to understand the semiconductor device. So this time we have two big topics. The first is EK diagram. Second is how to know how to explain the carrier numbers. So let's know about the EK diagram of topic 1. Before asking about the EK diagram, we have to understand of this K. As you know, the E means energy, but K is related to this A. In this case, you can just understand that positions has the atoms. So atoms are aligned. So we can get this between of these two potential energy gap. We can just say this gap A. So the K means 2 pi divide A. That K is similar to the W E pi divide T, which we learned in the signals and system class. So by redrawing the X and X domain to K domain, then we can get the period, the same period. So if we understand of only this period, we can understand the whole of thing. So that means a EK diagram. So let's see the two EK diagrams. The first K case of EK diagram, we can see that two lines. That line is valence band H, which is the top energy level of valence band, and that line is conduction band H, which is the lowest level of conduction band, and the highest level of this H and the lowest level of conduction band H, and between that gap, that is a forbidden band. And also band gap. In this case, the conduction band H and valence band H are same aligned. So we can see that EK diagram in gallium arsenide. The second EK diagram is a little bit different from before. We can also see that line and this line. So this is the valence band edge, and this is conduction band edge. Be aware that this is not a edge because this position is more lower than this conduction band. So we have to see this position. So the band gap is here, but there has a one problem. That is the difference of the before EK diagram. The alignment is different from this. We have this different from that position and that edge position. So let's call about this gap delta K. So that means if we only gives only band gap energy, the electron can't go up to the conduction band. It means it doesn't make excitation. So if we move electron to conduction band, we have to give the more energy than band gap energy. So that is the difference. So we can call this a case direct band gap, a direct diagram, ion band semiconductor. From this case, we can say that indirect. So silicon or germanium is in that case, indirect semiconductor. And let's know about doping. The doping has two cases, donor doping and acceptor doping. The same thing is that by giving some impurity, we can get more current flow than intrinsic semiconductor. Then let's see first about donor doping. The donor doping usually puts the impurities in group 5, but in this case we put the prosperon as an impurity. In prosperon, it has 5 electrons from peripheral electron. So if we doing covalent bonding with silicon, there has an extra electron in here. So we can call this carrier. And in donor doping case, the carrier is electron. The second case is acceptor doping. In this case, we usually using group 3 impurities, but we are usually using boron. The boron has 3 electrons of peripheral. So if we doing a covalent bonding with silicon, we have to get one more electron by somewhere. So there has a one hole in this silicon. So in acceptor doping, the carrier is whole. By doing some doping, we can by comparing to intrinsic semiconductor. Before comparing, we have to know about the concept of Fermi level. The Fermi level means the probability of electron can be exist 50%. So, on the intrinsic semiconductors, the Fermi level is just middle of the conduction band and valence band edge. But if we doping it, the Fermi level is different from intrinsic semiconductor. For donor case, the Fermi level goes up so the Fermi level is narrowing between conduction band edge and Fermi level. In acceptor case, the Fermi level goes lower. So by doping this, by just receiving a little energy, we can make to excitate the electron, and we can make a current flow more easily. And the acceptor case is also same. We can make a hole in valence band, so we can make a current flow more easily. So it is important to giving some acceptable doping so we can measuring or we can get a higher quality of semiconductors. Then that is a little bit another topic of the last compared to last two topics. We will say about how to know the carrier numbers. So before understanding this carrier number, we have to know about two concepts. The first concept is Fermi-Dirac distribution, and second is density of state. So let's see first about Fermi-Dirac distribution. The Fermi-Dirac distribution is related to the probability. Before knowing how numbers carrier exist, we can consider about two things. The first thing is state. If the state doesn't exist, no electron or no hole can exist. So first we have to know about how many states are exist. And second, we have to just know about how carriers are exist. But from carriers, it is electron or hole that is too small from nanoscale, so we can't measure it. We can't measure it. So we will consider the probability instead of just measuring it. So the Fermi-Dirac distribution is related to the latter. The former is density of state. So let's see about this graph first. This graph is related to energy and probability of carrier exist. For this case, we just understanding the probability of electron exist. So the temperature is, when the temperature is 0 Kelvin, we already know that in the valence band, there has all of the electrons, and up to the conduction band edge, there has only state and there doesn't have electrons. So the probability is 0. And in this position, the probability of electron is 100%. But the temperature goes up, it means the thermal energy gives some energy to electron. So the graph changes. Let's see this position. The first, when the temperature is 0 Kelvin, there has 100% of probability which electron can exist, but the temperature goes up by, the probability is a little bit decreased, and for the conduction band side, the probability is a little bit increased. For more understanding, I just flipped this graph. So for the 0 Kelvin, in this conduction band, this edge of conduction band, there has 0% of the electron can be exist, and the 100% of electron can be exist in the valence band. But the temperature increase, we can see this edge to compare to when the temperature is 0 Kelvin. So there has a little bit probability which can be exist electron in the conduction band, and from the valence band edge, the percentage of electron is a little bit decreased. So we can explain this by that formula. The Fe is related to this formula, and if we know that temperature and the energy difference, we can get the probability of which electron or electron can be exit. If the carrier is not an electron but hole, we just get by subtract from 1 to the probability of electron. Then let's know about the density of state. As I told that in this case we can know about the state. So in this case we already learned that in band gap there has no state and also doesn't have electrons. But in the valence band and conduction band, the state can exist. In 3 dimension, we can get the state by using this formula. As you see that, this is just constant number. This one is effective mass. It is also the constant number. So that means the state is related to the root of energy. So you can see that this graph is related to root function. Then by learned about the two things, we can calculate the carrier numbers. First, that is, as you see, the density of state, and this is Fermi-Dirac distribution. And by multiplying these two functions, we can get this graph. So by calculating this area, we can know about the carrier numbers. That means state also exists and the electron also exists. So by calculating this area, we can know how electron numbers exist in the valence band and conduction band area. So the formula is under here. So by multiplying the state and Fermi-Dirac distribution and integral by energy. So that means the electron numbers of what we are doped. We can also calculate the whole numbers by same formula. So as a conclusion, we can know the relationship about these intrinsic semiconductors, the electron numbers of intrinsic semiconductors, and extrinsic semiconductors of electron and hole numbers. By multiplying two things, it is always same the 2 times of intrinsic semiconductors electron numbers. That means if you know about only one thing about carrier numbers, we can also calculating of another carrier numbers. So that means how to calculating the carrier numbers. So this time we learn about the EK diagram and what is doping means, and we also know how to calculate the carrier numbers. So after this, we can combining the donor doped semiconductors and acceptor doped semiconductors and combine them, and we can make a p-n junction. So next time we will discuss about the p-n junction.